The story of the proton begins long before its name was even conceived, in a world where the idea of atoms themselves was still only a philosophical speculation. For centuries, ancient thinkers from Democritus in Greece to early Indian philosophers mused about the possibility that all matter was built from tiny, indivisible particles. These musings were little more than imagination, for they lacked the precision and tools of experiment. The atom, in its earliest conception, was an abstract ideal, a notion that beneath the surface of the visible lay a hidden architecture of indivisible building blocks. Yet this early vision planted a seed, one that centuries later would grow into a revolution of scientific discovery. By the late 19th century, science was beginning to lift the veil. The 19th century was an age of chemistry, when elements were being classified and organized into the periodic table by Dmitri Mendeleev. The periodic table's power came from its ability to predict chemical behavior and even anticipate the existence of elements not yet discovered. But beneath this chemical regularity lay a mystery. What was it that gave each element its unique character? Hydrogen, with its simplicity, stood apart, while heavier elements displayed more complexity. Something fundamental within the atom seemed to define its very identity, but the exact nature of this fingerprint remained unknown. At the same time, physicists were uncovering strange properties of electricity and magnetism. The discovery of the electron in 1897 by J. Thomson cracked open the atom for the first time. His experiments with cathode rays revealed a particle smaller than the atom itself, negatively charged and remarkably light. This was a breakthrough that changed the landscape of physics overnight. Suddenly, the atom, once thought indivisible, was revealed to have inner parts. Yet this revelation also posed a problem. If atoms contained electrons, which carried negative charge, what balanced that charge to make atoms neutral? Something inside must carry an opposite, positive charge, though its nature was not yet clear. Thomson proposed the so-called plum pudding model of the atom, where electrons were imagined as tiny negative particles embedded within a diffuse cloud of positive charge, like raisins suspended in a pudding. It was a bold step, but it was not the truth. The true structure of the atom would reveal itself through a series of brilliant experiments, none more famous than those conducted by Ernest Rutherford in the early years of the 20th century. In 1909, under Rutherford's supervision at the University of Manchester, Hans Geiger and Ernest Marsden carried out the gold foil experiment, a deceptively simple test that would alter the history of science. They directed a beam of alpha particles, helium nuclei stripped of electrons, at an ultra-thin sheet of gold foil. According to the plum pudding model, these heavy alpha particles should have passed through the foil with only slight deflections, like bullets piercing paper. For the most part, this prediction held true, but to their astonishment, a tiny fraction of the particles were deflected at large angles, some even bouncing nearly straight back. It was as though bullets had struck something solid and massive hidden within the atom. Rutherford, interpreting these results, declared that the atom must consist mostly of empty space, with its positive charge and nearly all its mass concentrated in a tiny central core, the nucleus. This was a revelation as dramatic as Copernicus suggesting the Earth moves around the Sun. The atom was no longer a featureless sphere of charge. It had a structure, with a dense center and orbiting electrons. The nucleus was born in scientific thought, and with it, the search to understand what resided within. Yet at this stage, the nucleus was still mysterious. It carried positive charge, but how? Was it made of yet smaller particles, or was it a single lump of something new? The answer would emerge in stages, through both experiment and theoretical reasoning. Hydrogen, the simplest element, provided the crucial clue. Its nucleus carried just 1 unit of positive charge, making it the lightest and simplest atomic species. Other elements had nuclei with larger positive charges, in whole, number steps. This suggested a universal building block of nuclear charge. Rutherford himself speculated as early as 1914 that hydrogen nuclei might serve as the fundamental unit of positive charge within atoms. If true, then the nuclei of all elements were built from multiples of hydrogen, like particles. This was the germ of the idea of the proton, though the term had not yet been coined. It was in 1917, during his studies of alpha particle interactions, that Rutherford achieved what could be considered the discovery of the proton. He observed that when alpha particles were fired into nitrogen gas, hydrogen nuclei were ejected. The logical explanation was that the alpha particles had struck the nitrogen nuclei and knocked out components identical to hydrogen nuclei. These ejected particles were positively charged and had the same mass as hydrogen atoms stripped of electrons. Rutherford concluded that the hydrogen nucleus was a fundamental particle present in all nuclei, and he gave it the name proton, derived from the Greek word protos, meaning first. In this way, the proton entered physics not merely as a theoretical entity, but as an experimental reality. The proton's discovery marked a turning point. It was not simply the recognition of a new particle. It was the recognition of the basic unit of matter's identity. Every element could now be defined by the number of protons in its nucleus, what we now call the atomic number. This insight provided the foundation for modern atomic theory. For the first time, scientists could explain why elements arranged themselves in the periodic table according to their chemical properties. It was the number of protons that determined the behavior of atoms. Hydrogen had 1 proton, helium 2, carbon 6, oxygen 8, uranium 92. This clarity tied together chemistry and physics into a unified picture of matter. But the journey was not finished. The early model of the nucleus, consisting only of protons, soon ran into difficulties. The helium nucleus, for instance, contained 2 protons, which should strongly repel each other due to their positive charges. Something had to hold them together. Moreover, the measured masses of nuclei did not match the simple sum of protons alone. These puzzles pointed to the existence of another neutral particle, a particle that would eventually be discovered in 1932 by James Chadwick, the neutron. Yet the proton remained at the heart of it all, the positive bedrock upon which nuclear theory was built. In the years that followed, the proton became an object of ever more precise investigation. Its charge, its mass, and its behavior in magnetic fields were measured with increasing accuracy. It was found to be remarkably stable, seemingly eternal on human and even cosmic timescales. Unlike the neutron, which decays outside the nucleus, the proton appears immune to such decay, at least within the age of the universe. Its longevity made it not just a building block, but the very foundation of matter's persistence. Without the proton's stability, atoms themselves would crumble, and the universe as we know it would never have formed. The birth of the proton as a concept cannot be separated from the larger narrative of the birth of modern atomic theory. It represents the triumph of experiment over speculation, the power of simple yet ingenious investigations to reveal hidden truths. From Geiger and Marsden watching alpha particles scatter on gold, to Rutherford identifying the hydrogen nucleus as a universal building block, the the proton's emergence transformed our understanding of matter at its most fundamental level. The once abstract idea of indivisible atoms gave way to a layered reality of particles within particles, each discovery peeling back another layer of nature's design. At the same time, the discovery of the proton was more than a story of physics. It was a story of human imagination, persistence, and curiosity. Scientists of the early 20th century were working without the powerful accelerators and detectors of today. Their tools were modest radioactive sources, thin foils, scintillation screens, yet their insights were profound. The proton's discovery was the fruit of minds that dared to ask what lies beyond the visible, what lies within the atom that all of nature is built upon. The implications of the proton's discovery rippled across science. In chemistry, it redefined the concept of atomic number and the meaning of the periodic table. In physics, it established the nucleus as a structured entity composed of particles rather than an undifferentiated mass. In cosmology, it provided a foundation for understanding the early universe, where protons were among the first particles to form after the Big Bang, setting the stage for the creation of hydrogen, atoms, and the birth of stars. The proton was no longer just a particle hidden within matter. It was a cornerstone of the cosmos itself. And yet, even as the proton came into focus, deeper questions were beginning to stir. Was the proton truly fundamental, or did it conceal an inner complexity of its own? Could it decay, and if so, what did that mean for the fate of matter? How did protons, with their electric repulsion, cling together inside atomic nuclei? These questions would drive physics forward through the 20th century and into the 21st. The proton, once thought to be a simple piece of nature's puzzle, would turn out to be an entire world within itself, a microcosm of quantum forces and particles. But that journey, the story of quarks, gluons, and the strong force, would only come later. For now, in this first act of its history, the proton stands as the particle that revealed the atom's true heart. Its discovery was not the end of the story, but the beginning of a revolution that continues to reshape our view of the universe. To follow the proton's emergence from the shadows of speculation to the clarity of scientific discovery is to witness the birth of modern atomic theory itself, the dawn of an age where the invisible became visible and the very fabric of reality was laid bare. The discovery of the proton may seem, in hindsight, inevitable. Once electrons were found, and once Rutherford's gold foil experiment revealed the nucleus, something carrying positive charge had to exist. But the path from speculation to certainty was neither simple nor straightforward. Each experimental clue had to be pieced together with immense care, and each new insight led to further mysteries. In this way, the proton became not only a discovery, but a doorway into the unknown. After Rutherford's identification of the hydrogen nucleus as the proton in 1917, the scientific community gradually adopted this new concept as fundamental. Hydrogen, the simplest atom, provided the perfect prototype, a single proton orbited by a single electron. Its simplicity made it a laboratory for theory, a model against which predictions could be tested and refined. It was in hydrogen's spectral lines, the discrete colors of light emitted when electrons changed energy levels, that Niels Bohr in 1913 had already introduced his revolutionary model of the atom, combining classical orbits with quantum rules. Now, with the proton confirmed as hydrogen's nucleus, the Bohr model gained a deeper foundation. The electron did not orbit an amorphous positive sphere, but a discrete particle with its own identity. The proton also revealed a profound regularity in nature, atomic number. Until the early 20th century, elements were arranged in the periodic table by their atomic weights, but inconsistencies arose. For instance, iodine and tellurium appeared in reversed order by weight, yet their chemical properties clearly demanded their current placement. The discovery of the proton provided the answer. It was not atomic weight that defined elements, but the number of protons in the nucleus. This was confirmed spectacularly by Henry Moseley in 1913, who used X-ray spectroscopy to measure the frequencies of X-rays emitted by different elements. Moseley showed that these frequencies increased in a precise way with the nuclear charge, establishing atomic number as the true defining property of elements. From that moment, the periodic table became a chart of protons. Every element's identity was written not in its mass, but in the count of its protons. This breakthrough tied chemistry and physics together in a single elegant framework. The growing understanding of the proton also raised questions about the forces at play within the nucleus. If protons all carried positive charge, they should repel each other strongly, especially when crowded together in heavy nuclei. And yet, nuclei held together with remarkable stability. What invisible glue bound the protons into a coherent whole? The search for this binding force drove nuclear physics for decades. While the neutron's discovery by James Chadwick in 1932 solved the puzzle of nuclear mass, it also deepened the mystery, for neutrons themselves were neutral and added stability without contributing repulsion. Together, protons and neutrons' nucleons formed the architecture of nuclei, but the force that held them in place, later known as the strong nuclear force, remained a riddle. It is worth remembering how limited the experimental tools of the early 20th century were. Unlike today's colossal particle accelerators, Rutherford and his colleagues worked with tabletop setups, radioactive sources emitting alpha particles, thin foils, and scintillation screens viewed by the naked eye. Their insights did not come from brute technological power, but from ingenious reasoning. The ability to imagine unseen particles, to deduce their existence from indirect evidence, was as much an act of creativity as of measurement. Rutherford himself once remarked that physics was a science where one could often learn more from a single experiment than from volumes of speculation. The proton's discovery exemplified this philosophy. As the proton became more firmly established, its properties became subjects of careful measurement. Its mass was found to be about 1/836 times greater than that of the electron, a disparity that emphasized its role as the atom's anchor of mass. Its charge was equal and opposite to that of the electron, ensuring overall atomic neutrality. These measurements gave the proton a dual character. On one hand, it was a simple counterpart to the electron, a particle with complementary charge. On the other, it was massive and mysterious, dominating the atom's weight and defining its nuclear structure. The idea of the proton as first, as its Greek-derived name implied, resonated deeply with the scientific imagination. In a sense, it was the first building block, the foundation upon which all nuclei were constructed. Hydrogen, with its single proton, stood as the elemental seed of the cosmos. In the furnaces of stars, protons collided and fused, building up helium and heavier elements through nuclear fusion. In this way, the proton was not just the building block of atoms on Earth, but the engine of cosmic alchemy, forging the diversity of elements in the universe. Although this stellar role would only become fully understood later in the 20th century, the seeds of that realization were already being sown. The cultural and philosophical implications of the proton's discovery were immense. For centuries, the atom had been considered indivisible, a final unit of matter. The very word atom comes from the Greek atomos, meaning uncuttable. The electron's discovery had already violated that ancient belief, but the proton drove the point further home. The atom was not indivisible but structured, with its own architecture and inner dynamics. Human knowledge had pierced through to a deeper layer of reality, only to find that reality itself was layered further still. Each new discovery revealed that what seemed fundamental was, in fact, composed of even smaller parts. The proton was celebrated as a fundamental particle, but whispers of its possible substructure already stirred. Could it, too, be divisible? The answer to that question would not come until the latter half of the 20th century, when the quark model revealed the proton to be a composite particle. Yet even before that revelation, the proton's discovery had already transformed science. It explained chemical identity, illuminated nuclear physics, and laid the foundation for quantum mechanics to merge with atomic theory. Its story was inseparable from the broader story of the atom's unveiling. The proton also became central to the technologies of the 20th century. Nuclear energy, in both its destructive and constructive forms, was rooted in the behavior of protons within nuclei. Understanding their interactions led to the splitting of uranium nuclei in fission and the potential for fusion energy by combining hydrogen nuclei. The balance of protons in the nucleus dictated stability and radioactivity, phenomena harnessed for medical imaging, cancer treatment, and countless industrial applications. The discovery of the proton had begun as an academic triumph of physics, but it quickly spilled into the fabric of civilization, shaping history in profound ways. In the laboratories of the early 20th century, the proton was more than just a particle. It was a symbol of the new physics, experimental, precise, and unafraid to shatter old assumptions. It represented the triumph of evidence over tradition, of observation over speculation. And yet, like all great discoveries, it raised more questions than it answered. Why did protons and neutrons stick together in the nucleus? What governed their interactions? Why was the proton stable while the neutron decayed? Why did protons have the mass they did? These mysteries propelled physics into deeper realms, into quantum mechanics, quantum field theory, and ultimately the Standard Model. But even within the moment of its discovery, the proton carried a poetic quality. The lightest, simplest nucleus, the single unit of positive charge, the first particle, train Urit mind, to be comfortable in limbed to capture something essential about the order of nature. The hydrogen atom, composed of one proton and one electron, became not just a test case for theory, but a symbol of simplicity, the starting point of matter. That simplicity belied the vast complexity that would later be uncovered within, but it remained a beacon for science. The birth of the proton was thus more than a scientific milestone. It was a turning point in humanity's quest to understand reality. It marked the transition from atoms as philosophical abstractions to atoms as scientific facts, dissected and described with experimental precision. It transformed chemistry into physics, binding the two disciplines in the shared language of protons and electrons. It linked the microcosm of the atom to the macrocosm of the stars, showing that the same particles found in the laboratory were also the engines of the cosmos. To appreciate the significance of the proton's discovery, one must also appreciate the intellectual courage it required. Rutherford and his contemporaries dared to imagine that the atom, long held as indivisible, could be penetrated, probed, and understood. They dared to infer the existence of unseen particles from faint flashes of light on a scintillation screen, to reconstruct the hidden architecture of matter from the trajectories of invisible projectiles. Their work stands as a testament to the power of human reason, guided by curiosity and sharpened by experiment. The proton, once hidden within the nucleus, emerged as a cornerstone of modern science. Its discovery was the birth of modern atomic theory, the moment when the atom was no longer a philosophical dream, but a physical reality with structure, laws, and mysteries waiting to be unraveled. It was the moment when humanity's gaze, once fixed on the visible world, pierced into the invisible heart of matter. The story of the proton's discovery is not merely a chapter in the history of science. It is a story of beginnings. It is the beginning of nuclear physics, the beginning of modern chemistry, the beginning of particle physics, step by step. And it is a reminder that within even the smallest things lies a power that can illuminate the nature of the cosmos. In the end, the proton is both simple and profound. It is a single particle, yet it defines the identity of every atom. It is stable beyond measure, yet it may conceal within it the secrets of decay and unification. It is born in the heart of stars, yet it resides in every cell of our bodies. Its discovery was a human triumph, but its significance transcends humanity. For in uncovering the proton, we did not merely find another particle. We found the power within, the essence of matter, the first step on a journey to the heart of the atom. The discovery of the proton revealed far more than just a new particle. It unlocked the very principle that defines the identity of matter. Atoms had long been considered the smallest units of the elements, and for centuries their individuality seemed mysterious. Why was hydrogen different from helium? Why was oxygen different from carbon? And why did these elements combine in such precise and repeatable ways? The answer lay hidden in the nucleus, and the proton became the key that turned speculation into clarity. To say that the proton defines atomic identity is not merely to assign it a role among particles, but to recognize it as the very fingerprint of the universe. Before the proton's discovery, chemistry had already advanced through the careful work of generations of scientists. Antoine Lavoisier, in the late 18th century, had given the first modern definition of elements as substances that could not be broken down by chemical means. John Dalton, in the early 19th century, revived the atom as a scientific concept, proposing that each element was made of identical indivisible units, and that chemical reactions rearranged these atoms into new combinations. Dmitri Mendeleev's periodic table in 1008-169 elegantly organized the elements according to their weights and properties, allowing remarkable predictions of undiscovered substances. Chemistry had created order, but the ultimate cause of that order remained elusive. The periodic table was a triumph of human insight, but it carried within it puzzles. When arranged by atomic weight, most elements lined up neatly with their chemical behavior, but not all. Tellurium, heavier by weight, came before iodine, though chemically it seemed out of place. Such inconsistencies pointed to a deeper principle hidden within the atom, something beyond mere weight that governed identity. The proton's emergence provided the solution. It was not the mass of atoms that determined their place in nature, but the number of protons in their nuclei. The proton count became the true marker of atomic number, the decisive quantity that distinguishes one element from another. This realization redefined chemistry at its very foundation. Hydrogen, with one proton, was the simplest and lightest element. Helium, with two protons, followed next, chemically distinct in its inertness despite its lightness. Carbon, with 6 protons, became the foundation of organic chemistry, forming the countless molecules that make up life. Oxygen, with 8 protons, gave breath to living creatures and energy to fires. Uranium, with 92 protons, represented the upper edge of naturally occurring elements, heavy and radioactive. SEND-DES, ING, SOR, and more STEPMES, ALSAS ESTHE. GES, azotic table, was no longer arbitrary. It was written in the language of protons. In this way, the proton is the foundation of matter's diversity. If all atoms were built from protons and electrons alone, without variation in proton number, the universe would be monotonous. It would consist of nothing but hydrogen, a bland sea of identical atoms incapable of forming the complexity of chemistry, biology, or even planets. It is the variation in proton count that generates the periodic richness of the elements. Each additional proton reshapes the electron configuration around the nucleus, altering how atoms interact, bond, and combine. The vast array of chemical phenomena, from the metallic luster of sodium to the reactive nature of chlorine, arises ultimately from the number of protons in their nuclei. The proton also grounds the very concept of atomic identity in something tangible. Electrons can be added or removed from an atom, turning it into a positive or negative ion, but the atom's identity does not change. Oxygen with 8 protons remains oxygen, whether it carries extra electrons as oxide ions or lacks some in highly charged states. Neutrons can vary as well, producing isotopes of the same element carbon-12 and carbon-14, for example, both with 6 protons, but with different numbers of neutrons. Yet isotopes remain the same element, for they share the same proton number. It is the proton that is the unchanging essence, the marker of identity, while electrons and neutrons provide flexibility and nuance. One way to appreciate this is to imagine stripping an atom down to its core. Remove all the electrons, and you have a bare nucleus. That nucleus still defines the element, still carries the charge equal to its proton count. Remove neutrons, and though the stability may change, the element itself persists until too many are gone. But remove even a single proton, and the element ceases to be itself. Oxygen with 8 protons becomes nitrogen with 7. Gold with 70. 9 protons becomes platinum with 78. To alter the proton count is to transmute matter, to change one element into another. This was the ancient dream of alchemists, to transform lead into gold, and it is possible not through mystical recipes, but through nuclear reactions. The proton number is the lock, and to change it is to open the door to elemental transformation. In stars, this transformation occurs naturally through nuclear fusion. Hydrogen nuclei protons collide under immense heat and pressure, fusing into helium and releasing vast amounts of energy. This process powers the sun and all the stars, and it is through such fusion that heavier elements are forged. Protons join to form carbon, oxygen, silicon, and eventually iron. Beyond iron, in the explosive death throes of supernova, protons and neutrons are rearranged to create the heaviest elements. The cosmic abundance of matter, the richness of the periodic table across the universe, arises from the way protons combine in the hearts of stars. Without the proton's role as a nuclear building block, there would be no chemical diversity, no planets, no life. The proton's role as a foundation also extends into the realm of biology. Life is built from molecules, molecules from atoms, and atoms from protons and neutrons bound together in nuclei. The proteins that make up our bodies, the DNA that encodes our genes, the oxygen we breathe, and the carbon that forms the backbone of organic molecules, all derive their properties from proton, defined identity of their atoms. Carbon's 6 protons give it the ability to form 4 bonds, a unique versatility that allows for the chains, rings, and complex frameworks of organic molecules. Oxygen's 8 protons create a strong pull on electrons, enabling the energy exchanges of respiration. Nitrogen's 7 protons create the chemistry of amino acids and proteins. Life's very architecture is written in the language of protons. To grasp how fundamental this is, consider a hypothetical universe without protons. Without positively charged nuclei, electrons would have no anchor, no orbit, no atoms. Matter, as we know, it would dissolve into a cloud of free particles, incapable of forming stable structures. Even a universe with protons, but all atoms identical, would lack the complexity necessary for life. It is the proton's identity, defining role, its ability to vary in count while retaining stability, that allows for diversity, chemistry, and biology. The proton is not just one among many particles. It is the foundation of the physical and living worlds alike. This recognition also transformed physics into a discipline that could explain the natural order of the elements. Before the proton's discovery, the periodic table was descriptive, a map of observed behavior. After the proton, it became explanatory, rooted in a principle of nuclear structure. The periodicity of chemical properties was no longer a mystery of nature. It was the inevitable consequence of increasing proton count and the resulting electron arrangements. Physics had given chemistry its foundation, and that foundation was the proton. Yet the proton's role went even further. It not only defined identity, but also set the scale of matter itself. The charge of the proton, exactly equal in magnitude to that of the electron, ensured that atoms could be electrically neutral. This neutrality allowed matter to be stable, preventing overwhelming forces of attraction or repulsion. The proton's mass, much greater than that of the electron, anchored atoms with inertia, giving them weight and substance. Without the proton's balance of charge and mass, atoms could not form the stable, tangible matter that makes up the physical world. In this way, the proton became more than just a particle. It became the very foundation of what we call matter. It was the fingerprint of identity, the origin of diversity, the anchor of mass, and the heart of stability. To discover the proton was to discover not just another piece of the atomic puzzle, but the central piece around which the puzzle fits together. And yet, this role of the proton as foundation also raised profound questions. Why is the proton's charge exactly equal and opposite to that of the electron? Why does the proton's number define identity rather than the electron or the neutron? Why is the proton stable when so many other particles are not? These questions hinted at deeper symmetries and laws of nature, laws that scientists continue to explore in the search for a grand unified theory. The proton is both a particle and a mystery, both a cornerstone and a doorway. The journey to understanding the proton as the foundation of matter is a journey into the very essence of the universe. It is a recognition that the diversity of elements, the order of chemistry, the reality of life, and the very existence of stable matter all flow from the number of protons in the nucleus. To understand the proton is to understand why matter is the way it is, why the universe is not a formless cloud, but a structured cosmos rich in variety and possibility. When we say that the proton defines atomic identity, we are speaking not only of its role in distinguishing one element from another, but also of its function in making matter recognizable and persistent, Identity is not just a label. It is continuity through time. The reason oxygen today is the same oxygen as it was billions of years ago. The reason hydrogen has remained unchanged since the first moments after the Big Bang is because the proton itself is stable, unyielding, and enduring across cosmic time. Unlike the neutron, which decays into a proton and electron outside the nucleus in a matter of minutes, the proton has resisted all attempts to find its decay. Experiments buried deep underground, in vast detectors shielded from cosmic rays, have waited patiently for evidence of proton decay, predicted by some grand unification theories. Yet no such event has been recorded. The proton appears to persist for timescales beyond even the age of the universe, a fact that gives matter its endurance. If protons were unstable, the universe itself would be ephemeral. Atoms would eventually disintegrate, their nuclei